Okay, so we will continue. We talked already about the basic concept. We will go very quickly over this again. So the system variables can be classified in kinematic and kinetic variable. So kinematic are going to be displacement and flow. So if you have a linear motion, so displacement is going to be the position with respect to our reference, and the flow will be the speed of that block moving in a given direction. So for kinetic variables, then we will have the effort and the momentum. The effort will be the force we apply to the block, and the momentum is, in that case, the mass multiplied by the speed. So that's a classification for any system. We can have these four type of variables, and here I have three examples. The linear example that I already described here, but also we can have a rotational translation, and we will apply this in the case of generators in the power grid, or also, because we know this very, very well, this can be applied to electrical circuit as well. So the kinematic variable then, for the case of electrical circuit, is going to be the displacement is going to be related to the amount of charge, and the flow is going to be the current. For the translational system, I already talked about it, and the rotational system, the displacement is going to be measured with respect to the angle, with respect to a reference, and how fast changes is going to be the flow, which is the rotational speed. For kinetic variable, then, as I said, you have the force as an effort for this linear translation, and the momentum is going to be mv as the linear momentum. So as we know, there is a relationship between the variables. So the effort is going to be equal to the derivative in time of the momentum, right? Does it make sense? So the derivative of this with respect to time, as the mass is constant, is mass times the derivative of the speed, which is acceleration. And this is the Newton law. Effort equal to the derivative of the momentum. But the same thing can be applied to the rotational system. In this case, the effort is going to be the torque, and the momentum is going to be the inertia times the rotational speed. And similar equation we obtain here, torque is equal to the inertia multiplied by the derivative of the rotational speed, or the acceleration of. For the electrical system, then the effort is going to be the voltage, and the momentum is going to be the flux linkage, which is L times the current. So that is nothing else than the law of induction. So we were here, I think, and these are basic definitions for work, power, and energy. So the definition for work is done in this fashion. An incremental value for the work is going to be equal to the effort that for that amount we consider constant, multiplied by the small increment in the displacement. So that's the definition we have from physics, maybe from the first year in the program. But we can work with this definition now. So one thing we can do, because already we discussed this, that the effort is equal to the changes in time of the momentum. We can replace the definition here, and then we can do this mathematical trick in which the derivative of this increment in the time can be passed on this side of the equation. So you have dp multiplied by the derivative of q in time. And the derivative of q in time, q is the displacement, that is nothing else than the flow. So alternatively, this definition can be expressed in this fashion. This is the one that we study in physics for a year, but it's an alternative. So this a small increment in the work we will have can be determined as the flow multiplied by the increment in the momentum. So with this definition, now we can obtain the derivative of this in time, because the derivative of this will give us the power. So we take either this equation or this equation, and we need to divide it by dt, the increment in time. So with that, we obtain a definition of power. So if we use this, then this expression divided by dt will give you the effort multiplied by the flow. So in an electrical circuit, that's what we have. Power is the effort, voltage, multiplied by the flow, current. Voltage and current will give you the power. But this can be applied to any system. So if you have a machine, then what is the power we will have in the machine? You have a synchronous generator. So how will you calculate the power? What is effort, torque, and the flow is the rotational speed. So for a rotational machine, don't forget this, the power will be nothing else than torque multiplied by the rotational speed. So we can apply these to any system. So it's a good thing that you can review these and use it. For the energy, then, what we need to do is to get the integral of the power in time, and then we can use this equation we have obtained so far. Here, as a summary, then I have the mechanical linear translation, rotational translation, and electrical circuit, and we have for each of them, I have the differential in work, the power, and the energy between two periods of time. And this is how we determine. Probably you remember this one for linear motion. Probably you remember this one for electrical circuits. So specifically, because this energy is obtained using the flow, this is energy we store in an inductor in the form of current. This is the kinetic energy in the linear movement, and this is the kinetic energy in the rotational movement. So all these energies are related with that flow. But we know that there are other components that behave different. So the other component, one that we know very well, is the capacitor. But in this case, the relationship between the fundamental variables is different. So what is the fundamental variable for this equation when we use flow? What we are assuming here? Are you ready?
Using charge.
Momentum is proportional to the flow, right? Momentum proportional to the flow. In an inductor, do you have that? Yes. What is the momentum? Flux linkage as proportional to the flow. That's the fundamental relationship. And when you obtain the energy, the power, and all the other definitions are given for this type of physical behavior, you will have that type of energy stored. But in a capacitor, you don't have this relationship. So for a capacitor, we will have a different relationship. What is that relationship?
Effort and displacement.
Effort and displacement. So for the capacitor, then we need to come up with a different thing. So in this case, we will assume that there is a linear relationship between effort and displacement. So that's happened for the capacitor. You know the equation very well. But the same thing can be applied in the linear translation and potential translation. Yes?
Sorry, I was going to say, yeah, but the spring also has a, I'm sorry, I didn't see that on the slide. The spring also has a linear relationship between effort and displacement.
Yes. So this is the type of energy that we will store in this component. And if you think about the equation, this is potential energy, right? Potential. You have potential energy in the capacitor, but in any type of spring. So we will have energy that is related with the flow, kinetic energy or potential energy. But there is another type of energy that is not stored but consumed. That is the dissipated energy. And we know very well for the electrical system that this dissipated energy is related with the Ohm law. In the assumption here is that there is a linear relationship between effort and flow. That's a relationship. So voltage is proportional to the current. But the same thing can be applied to the rotational movement and the linear movement. Yeah? So all these definitions can be applied to actually any system that we might have. We will deal with this. That's why I'm putting there this definition right here. Okay? Any question? Yeah. We will move to the next chapter then, and here we will start building the foundation to understand dynamic behavior in a system. And we will start with linear systems. So the first thing that I would like to discuss with you is that most of the time, and you did this in the first year in the program here, we consider one differential equation of high order for whatever system you're dealing with. And probably you study the second order differential equation, in which you know that the behavior of that second order system can have some sort of oscillations, and the solution of the system will converge to some variable. And you study that very well, and you find some nice tools to study those kind of equations, how to solve the equation. But in this part, what I want to talk about is how we can convert that simple equation we may have into something that is simple. Then this simple representation is going to be a set, not just one equation. We're converting this one equation with high order into a set of first order differential equation. Why we're going to do that? Because solving a first order differential equation is way much simpler than dealing with a higher order equation. So how we can come up with a linear representation of this, and this is what we're going to do here. So we will start with this equation, high order, whatever order you have there, and that's the goal. We want to convert this into a set. How many equations do we need? Well, it depends on the order. So if you have an n order differential equation, you will need n equations. And each one of these equations is going to be of first order. And then the step one, when we have this single equation, the first step we're going to do, we're going to take the higher order in the equation and isolate it. So we will take all of these terms and send it to the other side of the equation, as you can see it here. So that's the first step. Second step to obtain this linear representation is going to define the state variables. These are going to be the variables, relevant variables of our new linear formulation. So how we're going to define this, we're going to define the state variable starting from the order 0. So this differential equation you see at order 0, first order, n minus 2, n minus 1, and n order. That has to do with the number of times you differentiate the variable. So we will start with the order 0 and define that as a state variable. The second is going to be the first derivative. And we will continue in that fashion until we get the n minus 1 derivative. And that is going to be our last state variable. So first we obtain this explicit expression for the n derivative, then we define the state variable. Third step, we're going to differentiate each one of these equations. So when you differentiate this, what you're going to get? The derivative of x1 in time is going to be equal to the derivative of b in time. But what is the derivative of b in time? Nothing else than x2. So when we start differentiating this, we will start finding relationship between the variables. So the derivative of x1 will be nothing else than x2. If we get the derivative of x2, that will lead us to the second derivative of b, which is x3. So the derivative of x2 will be nothing else than x3. And we will continue in that fashion until we arrive to the last variable. The derivative of xn is going to be the n order derivative of the function. I forgot to put B of t. But when we arrive to the last expression, we cannot express this in terms of any other state variable, but we already have that definition, which comes from the single differential equation we have at the beginning. So when we come to this last derivative, basically, we need to replace all of these into the last equation we will obtain. And that's what we have. So we take the state variables, we differentiate the state variables, and we start finding the relationship. So this is going to be equal to x2. This is going to be equal to x3. This is going to be equal to x4, and so on, until we arrive to the last state variable, and we derive this, but this is nothing else than the first differential equation we obtained. This term here is going to be the excitation of our equation, as the name we give to this. But as you can see here, B is the state variable 1, x1. This is going to be x2, and so on until we arrive to the derivative xn. So this last equation can be expressed as a linear combination of all the state variables plus the excitation. So if we put all of that in matrix form, we have something like this. So the derivative of x1 is going to be this row multiplied by this column. This is the column of the state variable. So as the row has zeros everywhere except the second column, this is going to be nothing else than x2. So you have x1 derivative. One thing is that the derivative of a given variable xi can be also expressed with a dot on top. Yeah? So it's the same notation. So x1 dot, which is the derivative of x1 in time, is going to be equal to x2. So for x2, we will have something similar, the derivative of this, but in this case, all of them are zero except the third column. So x2 dot is going to be equal to x3, and we will continue in that fashion. When we move to the other variables, we observe that everything is zero, except these terms that are above the diagonal that are 1. Only those that are above the diagonal are going to be 1, until the last equation. In the last equation, basically, we have the coefficients of our single n-order differential equation from our system. Because the input or the excitation only show up in the last equation, everything else here is zero except the last term. U will show up just in the last equation we have here. So in the definition of the differential equation, I didn't say this, but I need to say it. We have here initial condition. When you have an n-order differential equation like this, we need to define what is the initial condition for all the derivative until n minus 1. So when we formulate a linear representation for this system, we need to express also what is the initial condition for each one of them. So x1 is going to be the variable b, x2 is going to be the derivative of b, first derivative, and so on until the n minus 1 derivative. So you need to know each one of these values. So what we obtain finally is a system that is one single equation, but with high order, and we transform that into a set of n linear equations, which is going to be much simpler to solve. That's the idea. Now, as you can see, we need to work now with matrices and vectors. So this is going to be a column vectors of n terms. It is going to be a matrix, n by n. And this is going to be another column vector of n terms. And in this case, because we have just one excitation, this is just going to be a scatter. But in other systems, this term can be more than one. Then you might have here two inputs, and then this matrix B will have two columns, and this can be expanded, of course. When we express this in compact form, instead of writing all these terms, we just can write this. But here we understand that X is going to be a column vector with a given number of terms. A is going to be a square matrix, n by n. And if you have one input here, B is going to be a column vector with n terms. Yeah? And the same thing for the initial condition. For the initial condition, we need to know at what time we know the state variables, because the system needs to include that point at that time. And from there, the variables will change over time according to the dynamics. So the first step is this one. How we convert an n-order differential equation into a linear representation. So the trade-off here is that we move from one variable, b, to n variable. But this is linear, and we can solve it easily. Example of this, you know this system very well, RLC. And when you study this system, probably you memorize the second order differential equation for this system, which is right here. And probably you remember the meaning of these parameters, right? RLC, but you remember the meaning of this. I hope so. What is the meaning of this? L over R. What is R? It's a component that dissipates energy, right? So what is the meaning of LR? Yeah, attenuation or damping. You remember the damping? And then you have another one, which is 1 over LC. What is that? Oscillation. The square root of LC is the natural frequency. You remember this term now? So you study this and use a second order differential equation, and you understood based on this coefficient if this system was going to oscillate or not, and what was going to be the frequency of the oscillation. Well, the square root of that, right? And you determine that, and then if you have oscillation, are these oscillations going to be damped and died at some point? Yes or no? Yes. Well, it depends on this coefficient that you have here, and how fast. That's the time constant of this attenuation or damp, right? Well, that's what you study, but as an example, what I'm going to do here is to show you, well, how we can study this in a different way with the linear representation. Yeah? So, when you study this system also, you will assume that at some point, in this case, time 0, you know how much energy you have in that capacitor as potential energy. So also you know how much current is going through the circuit, and you know how much energy the inductor has at that point. So based on those two things, you want to know how these variables, current and voltages, will change in time. And because you have a resistor here, this current and voltage will eventually die to 0, right? Because the energy you will have in the capacitor and inductor will be consumed by the resistor. And at the end, you will have no current, no voltage. No matter how much time we wait, that needs to die. One particular case is when the resistor is 0. In that case, what you will have here, you remember? Well, you look at the equation, then you don't have any damping. So what you are going to have a system that oscillates forever, right? Of course, we do not have that in practice because you cannot have a conductor that has zero resistance. So you build something in the lab, it will always die at some point. Okay, so how we're going to do it, let's apply the same thing that we discussed so far. So we have one differential equation. What is the first step? You isolate the highest order term we have, which is this one in this case. So we will take this, let's use this equation. Let's take these two terms and send it to the other side. The excitation in this system is this sinusoidal source, which is ET, and we're supposed to have that as an input data. So the first step, we isolate for that term, and then we define the state variable. We start with the zero order. So IL is going to be x1, and the first derivative of that is going to be x2. It's a second order system, therefore you have two state variables. When you have this definition for the state variable, you get the derivative of each one. So the derivative of x1, which is x1 dot, is going to be nothing else than x2. So x1 dot is x2. But when you get the derivative of x2 here, you get the second derivative of the common. But we have already an expression for that, and we replace it here. And by looking at this equation, IL is x1, and the derivative of IL is x2. So finally, you obtain two equations that are linear. The derivative of x1 is equal to x2, and the derivative of x2 is a linear combination of x1 and x2 and the input, the derivative of the input. We can present that in matrix form, and that is a state space representation for this RLC circuit. So this is going to be given. This is the vector B, which is a column vector. This is the matrix of the system 2 by 2, and this is the vector of the state variable. What you have here is the definition, the model of how these state variables will change in time at the derivative. And of course, we need to include the initial condition. So for this system, we know at a given time, T0, how much is the current and how much is the voltage at the capacity. In this equation, because all these state variables will depend on time, they change in time. It's too much to write this T all the time, so we will just drop this, and we will understand that whenever you see a state variable, that will change over time. So we will drop this T there and there. So that's the sample. Now, is that look simpler to you or not? Well, we should hope so. Well, I'm telling you that it's going to be simple. We will see that. We haven't shaded that yet.
It's better than the alternatives.
It's better. Imagine you have the power grid and you have, what is the order? Easily, I show you the variables, the state variables. We're talking about thousands. There is no way we can solve an equation like that. So the only alternative is to change this to a linear representation. Yeah. Is the only way we can define a space representation for this system that looks like this? Another way to ask this. Can we have a different representation for the same system? And why is that? This definition is arbitrary, right? Kind of, not completely. But the truth is, yes, if we define this in a different fashion, we can come up with a different representation. Which one we're going to pick is up to us. So for this system, for example, we can have a different representation by not even working with the second order differential equation. Most of the time, we will not know that simple equation. For example, for the power grid, we will not deal with that. So how we're going to do it? We're going to just use the fundamental equation we know for the system. So in an electrical circuit, how do you get the fundamental equation? what do you need to do? You remember the nodal technique and the mesh techniques for circuit analysis? You get that by Kirchhoff law, right? So you see how many loops you have and how many fundamental loops. Well, you need one equation for each fundamental loop. Then you look at the nodes. Well, you need one equation for each node. And you define the fundamental equation of your system. So we can do the same thing here. And if this is the system, what are the two fundamental equations you need? One is Kirchhoff voltage law. This voltage is equal to VR, VL, DC. That's one. Another one that is implied here, we don't write it, but it's implied, current Kirchhoff law, which means that the current is the same for the three components. Yeah? That's trivial one. But the last one, which is fundamental, is the behavior of this capacitor. These store energy in the form of potential energy. So we need to know how we describe this. What is the fundamental equation of the capacitor? The current is equal to C times the derivative of the voltage in time. So we will have two fundamental equations here. One is voltage Kirchhoff law, and the other the capacitor. I didn't even have to remember the second order differential equation. I just formulate the fundamental equation. So we can do that, and here they are. This is the equation for the current, and the equation for the capacitor, and the Kirchhoff equation. So now that you have the equation in that fashion, how you can define a state variable? Maybe you pick, for each differential term, you pick a variable. You have a differential term for the current here. Well, the current can be one state variable. You have a differential term for the voltage. Maybe the voltage can be another variable. So we can define here, for example, X1 can be the voltage of the capacitor, and X2 can be the current of the inductor. Does it make sense? Yeah, it's simple. And why would we like that too? Because we know that voltage is related to the energy stored in the capacitor. So that makes perfect sense. And in the inductor, the current is related to the energy stored in the inductor. So that makes perfect sense. Okay, so if we use this as the definition of the state variable, then we can obtain what is the representation for these two equations. So in this case, it's easy because this is going to be x1 dot equal to x2 dot, no, x1 dot is equal to x2 divided by c. That is exactly what we have in this first equation. X1 dot, which is the derivative of voltage dc, is equal to x2, which is the current in the inductor, divided by c. X2, the current in the inductor, divided by c. And in this vector, we have 0. So with the first row here, we have the first equation. Second equation, here, second row. The derivative of x2, which is the derivative of the current, needs to be equal to negative RL, R over L, multiplied by x2. That's what we have right there. This is IL, negative of RL. And then you have BC. So you have this on this side divided by L. You have negative 1 over L times BC, which is x1. That's what you have right there. And finally, you have this excitation E divided by L. That's what you have right there. So in this way, which is make more sense to us, because we don't need to memorize what is the differential equation of your system. If you formulate the fundamental equation for your system and then you define the state variables properly, you can come up with a different representation. Will this be able to describe the system? Yes. Will describe the same dynamics that the previous system we had. Yes?
When you show shows x1 equals b and x2 equals c. How did you choose that?
We look at the differential terms. So this is an easy way to do it. Each differential term, you see, you look at the variable, that's your state value. Okay?
Okay, and then you set everything equal.
And then you isolate for this term from this equation, and that's how you get the second equation. And then the same thing here. You isolate this, which is simple in this case. You just divide by c, and you get the first equation. Look at the first order differential term in your set of equations. Yeah. Physically, this is related with the stored energy. And we look at the system. By looking at the system, you know immediately the system has a second order or has two state variables. Why? Because you have two components that can store energy. Now that we have the representation, we have about 12 more minutes. Now that we have the representation, remember the compact form is this one. These are not scalar equations, these are matrix equations. So what you have here for x is a column vector. How many terms? It depends on the order of your system. So in the example that we have a second order, two state variable. So this is a column vector of two terms. And this is a matrix of 2 by 2. And because you have just one input, this is a column vector of two terms. And then you have initial condition, a column vector of two terms. Now, we're not going to prove this, but the solution for this system that I told you that was a simple model that we can obtain for this system is given by this expression. This expression has two components. The first component, as you can see, depends on the system matrix, which is 2 by 2 in our example, the initial time and the initial condition. It doesn't depend on the input right here. Because it doesn't depend on the input, we call this the zero input response. That's the name. So basically, this part of the solution will tell you how the variables will move if we start from the initial condition and we let the system go. For example, in the RLC circuit, we have this, a resistor, an inductor, and capacitor. Basically, we are going to have a short circuit here. We will have an initial condition for the current and for the voltage, and we will see how the variables will move in time starting from that point. But there is no input, there is no excitation. So that's a zero input response. What do we want when we do this? Maybe we want that the variables reach quickly the steady state value. That's what we want. What we don't want, which will never happen in this system, is that this can blow up and we lose, we call it stability. It will never happen because to have that, you need to have a negative resistor. That's not possible. Yeah. But if you have a negative resistor, these can grow and oscillate, but grow and go to infinity. That would be cool. Maybe with power electronics, we can create a negative resistor, but not with a physical resistor. The second part of the solution is this one. It's some integral. You need to get this the exponential of a matrix. Do you know what is the exponential of a matrix? Any clue?
Matrix has to be squared. It's just when you just take a matrix and you multiply by itself.
For example,
Oh, that's what you mean. A matrix in an exponent.
Oh, wow. I think I saw it before.
Same.
and we multiply by t. You know how to do that?
Nope.
Nope. Well, that's a big question. how we do that. That's hard, not easy. There is a lot of theory, mathematical theory to get this, that we will not review. In a grad course, probably we will review this. But we need to at least appreciate it that that's the type of solution we have here. We're not going to deal with that. Now, do you have any guess what would be the solution of this? What is the difference? The matrix is different. Probably this is too small for the camera. So in one case, I put this. What is the solution of that? We don't know. But another case would be, how much is that? We also don't know so far, but what would you guess?
Does it have anything to do with the determinant?
It's usually a good guess, yeah.
Yeah, we can start with that one. Huh? Well, the solution of this is going to be, because this is a diagonal matrix, it's going to be easy peasy. Well, that's easy. You might say, okay, I can see that. We need to prove that, but if you have a diagonal matrix and you get the exponential of a diagonal matrix, that's what you are going to get. Are you going to get the same thing here? No, that's hard. Okay, but that's this equation is trying to give you a solution for that. That's not easy, but that's the general solution for any system actually. If you are able to solve this, you have the solution of this. If we separate the thing, because this is a linear system, in a linear system, you can study this independently. One thing you can do, you assume that you don't have any input, and you calculate this part first. And then you assume that you don't have any initial state, and you calculate this part as a second part. And then you add the two solutions, and that will give you the solution xt. If there is no input, that's the zero input response. So these disappear from the system, and all that you have is that first part of the formulation. The derivative of the state variable is equal to a times s. And you consider the initial condition. Well, in this case, the solution is going to be this solution. Do you agree with me here or not? Is that the solution of a linear system? Probably you have not dealt with matrix equation before, but you have dealt with scalar equation. So if you have this is scalar, which is one real number, and you have this, what you see in this equation, that the variable you are trying to solve, if you derive that variable, is equal to or is proportional to the same variable. Okay? So if you have x squared and you get the derivative of this, how much you get? 2x. Is 2x proportional to x squared? No. Well, that's not a function that fulfills this. So what is the only equation, mathematical equation that fulfills that specific requirement? That you get the function, you get the derivative, and the solution of the derivative is proportional to the function itself. Exponential. Exponential is the only one that can do that. So when you look at this, you say, x needs to be exponential. And you propose a solution for this. What is the solution? Well, x of t needs to be with some k and some alpha t. Because if you get the derivative of this, then you get alpha times k e alpha t. And this is x. So the derivative of x is proportional to x itself. That's the only mathematical equation that can do that. So How much should be alpha if you look at this equation? Two. So we have one part, x of t is k exponential of negative 2t. Now, how much is k? I didn't put it here, but we need to have some initial condition here. Let's say it's 0. So if you evaluate this at 0, how much you get here? 1. So x of t of 0 need to be equal to x0, and that is equal to this. So k is x0. So what is the solution for this? Xt is x0 exponential of negative 2t. Yeah? That's the scalar equation. Now this is a little bit more complicated because this is not a scalar equation. It's a matrix equation. But you can see that the same applies. The solution for this is going to be the exponential of a t minus t0. Why? Because the initial condition was applied at t0. So that changed a little bit. And all of this is multiplied by xt0. Okay? Are you with me so far? Yes? So the only question here is, how can we obtain this? We are not there yet. These can be hard if A is a full matrix or a complicated matrix. This is not easy. And we will study a way to get this. Okay? We're getting there. The second part is solving for this. How you solve for that? You assume that the initial condition is 0. You just need to solve this integral. So the system in that case, when the state is 0, you solve for this with this equal to 0. So that's the case. And then the solution for that comes from solving this integral. So you need to do a lot of work here with the exponential of at and get the solution of that. In this course, we will not deal with this part. Yeah? This can get complicated. So how we're going to solve for this? We're going to use numerical techniques. Okay? But in this course, we are going to care about this. Why? It's not because we want to get the solution for this, no. We want to get the solution for this because we want to understand what is going to be the natural response of the system. If the system starts from an initial condition, is the system going to behave well or not? That's why we're going to study this part. So for simplification, we will assume that this part, we don't want to solve it until we study numerical techniques. But this part, we want to understand what is the meaning of this and how we can anticipate whether the system will behave well or not. Okay? So we will leave until here, and next week we will deal with the matrix and eigenvalues and eigenvectors. And I already put in Canvas a MATLAB file that can explain what is an eigenvalue and eigenvector. Take a look at that. We're going to use that on Monday. Yeah? And remember, there is a quiz on Monday that will cover everything we discussed this week from Monday to Friday. Yeah? Thank you, guys.